Yeah. So, okay, now, thank you for the opportunity for this talk. So now I see that I have I have wrote the title too general. I am not talking about such, for very general transport properties of Weyl semimeter, but some special cases of that. So this work I have been done, I have been doing for a long time with Arijit Kundu, Ritojit and Rohit, all from IIT Kanpur. So, as we know that it is for the general audience, I want to spend a little time with the basics. So, let me start with what are the topological properties, topological materials, and what are the topological properties of them. So, topological properties are those properties, those are robust against the continuous deformation of any, material. So, and one of the feature that one can see in those topological materials is that a bulk boundary correspondence is that the feature of the bulk is reflected in the boundary. So, for the simplest example, one can think of a quantum Hall system where one can have a 2D metal and electric field piercing through it in a perpendicular direction. So, what happens is that in that the bulk band structure gets gapped. It's an insulator in the bulk, but in the edge one can see a current flows throughout persistently. So that we call the edge current, and the number of edge current and the charge it actually carries is quantized in that case. So this is one of the most simple example of a topological property, and how many edge modes will propagate, that depends on where one puts the chemical potential is. So now one can go into a much more general scenarios where one can consider that what is this analog of 3D of this 2D structure is the automatic answer would be the topological insulator. In that case also one have the bulk gap, and there are the current carrying surface modes. Now okay, so now I can actually go into the particular material that I have been studying over the time. It is called the Weyl semimetals. It's Weyl semimetal because of the fact that okay, it has the bulk gap, not throughout. There are some points where the valence band and the conduction band, they touches each other. And these touching points, they are called the Weyl nodes. Why is that? Because very close to the Weyl nodes, the electron actually follows the relativistic Weyl equation, and it has two chiralities kind of going rightwards and leftwards, that we can see here that it goes rightward and inward, and this is called the point of charge neutrality where the bands touch. Now okay, so now with a lot of features, so one of the most interesting feature of these Weyl points is that they actually carry a definite chirality. That means they can act as a sink or source of a Berry curvature. Now in a finite geometry, and in a periodic, if one considers a periodic sample, periodic boundary condition, a Weyl point with a single chirality can't appear. It must appear with the opposite chirality. So 1, 3, 5, this number of Weyl points, Weyl nodes are not possible. So it has to appear with 2, 4, 6, all 2n numbers of 2n numbers. So that one has to be a positive chirality Weyl point and it has to have a negative chirality partner. Now these topological characteristics, the chirality that I have been talking about, it has all kinds of features. This one can say the chiral anomaly one can see in these kinds of materials where the number of particles in the presence of electric or magnetic field is not conserved near one Weyl node. But what I am much more interested in, one particular feature that one can see if one has a finite geometry. Now here we have a finite geometry, finite slab of a Weyl semimetal, where we can see is that it is actually finite in one direction, let's say it's z, and in other directions it is infinite. Now, as other directions are infinite, the momentums in those directions can be considered to be a good quantum number, whereas in the z direction, the momentum is no longer a good quantum number. So that is what I had to, I mean, one has to choose this curious set of coordinates where the position coordinate in the z direction and the momentum coordinates in the plane. So what happens is that now, so if one have a plane, I mean, imagine a plane just perpendicular to the connecting vector between the Weyl points, one can get a Chern insulator. So what is a Chern insulator? So if one calculates the Chern number of this particular plane, on this particular plane, they will get some non-zero Chern number. Now it is very similar to what we had in the case of quantum Hall effects, except that there is no magnetic field. This particular vector is breaking the time reversal to make the H current. Now, if one considers a set of parallel kind of these planes here, one can have in the z is equal to L part, that a particular line of state that actually propagates in one direction. So that state, that arc-like state that forms in surface, is called the Fermi arcs. And these Fermi arcs, so in this surface one has a one Fermi arc, and the other surface one can have another Fermi arc in propagating in opposite direction. Now, one can actually putting the boundary conditions appropriately and solve this particular. This is one model I have chosen. This is a time reversal symmetry broken model. And so here we see that there is one near the zero energy, one has one band and other bands are there. So near the zero energy, from this region, one can have the Fermi arc states lying here. And from the other angle, one can see that the Dirac cone, the Weyl cone-like feature coming up. Here are two particular chiralities are there. They corresponds to right moving Fermi arc and the left moving Fermi arc. Okay, so now my interest is that how much these Fermi arcs actually affect the transport, electron transport in a particular Weyl semimetal. So let us have some one slide on the disorder averaging. So it's that we have randomly situated impurities throughout the material, and the disorder density is pretty small compared to the particle number density here. So now what we have, that scenario that if electron comes and affected by the potential, external potential posed by the disorder points, and then get scattered. Now, in the case of a disorder scattering, to wash out all the phase coherence coming from one disorder, one collision with a disorder, one has to do disorder average. And if one has to do disorder average, at least the first non-trivial order that actually contributes is the two scattering events, and that will give rise to this kind of effective diagrams. Now, if one have calculate the self energy from the effective diagram, that from the self energy one can have the finite lifetime of the scattering events, and that actually contributes to the resistivity or the conductivity of the material. Now, just one feature is that, so there are two parts here. So this part is important. This is actually the form factor, one calls a form factor, and it is actually the wave function overlap one can have from the disorder scattering. So now we are in the linear response regime. So our conductivity is defined to be something like this. And if we do all the technicalities, we are left with this equation. So where this is a Fermi function, and this Fermi function tells that all those bands will okay, so let's say that these A, B's are the band indices, and alpha, beta are the XY indices, that in two directions we are seeing the conductivity. And what it says is that all those bands will actually contribute to the conductivity is what lies between -nu and 0. And what happens is that, in the case of the Fermi arcs, we see that it propagates in a particular direction. So that actually apparently breaks the isotropy in the xy plane. So we can't expect that sigma xx would be equal to sigma yy. So now the results. So in the results that I can say is that, okay, so it has two features. One, so this mu is the chemical potential, that where we actually set the chemical potential somewhere near the band here, that when we puts it here, it will just include the surface states, and when puts it higher, it can include the bulk states also. And typically the bulk states actually propagate, the separation between the bulk state is of the order of 1 by L. It's actually pi by L, so one can say it's a 1 by L. So this feature actually has been shown, first, by Hosur, Paramesan and Vishwanath, but in that case, they didn't consider the finite geometry, they considered the infinite slab geometry. So it has two parts. One is there is a peak at zero frequency, and there is a rising up, there is an upturn, and after that the conductivity starts to rise. So this peak is called the Drude peak. So it is the DC conductivity if one measures in an experiment. This is the peak they find at zero frequency. And after that, with this, what this upturn is happening is that this is actually from the interband scattering events. So now here I separately plotted these upturn parts for very small number of bands and different lengths. So you see that for the sigma YY case, we don't see any dependence of this upturn point on the thickness. But in the sigma L, there is one dependence of the upturn point on the thickness. So this is, one can see is that in the Y direction, that is this direction. So from where the upturn will take place, it's of the order of 2 mu. Mu is the chemical potential. So after that, all the interband scattering starts to take place. But in the case of the X direction scattering, so we see that in the 2 mu, where the second band lies, I will take 2 minutes just. Second band lies is not a relevant parameter for this. We have to take account of the scattering events between the surface bands and the next bulk band. Now this next bulk band for different length actually shifts by 1 by L. So this dependence on the L that comes into this upturn part. Okay. So now what we have done is that we took separate different K0. It's not coming here, the colored word. So different Fermi-Arc length. K0 is the Fermi-Arc length of the Fermi-Arc, and see that how it changes with the thickness. And we see is that it rapidly increases, and the thickness is actually then it becomes slower. That we can see from calculating these kinds of thing that we actually ambitiously called beta function, but okay. So it actually saturates to one value. It is because of the fact that when as one increases the thickness, the Fermi surface, apparent Fermi surface of the scattering event, number of scattering event also increases, and the transport mode, number of transport mode also increases. So competition between them actually leads us to there. So now one can do a estimation by having a simple model of the Fermi arcs and see the same feature comes up. There is one difference because of the fact that in the real model, when one changes when one decreases the thickness to very small and then a small gap appears, that it doesn't capture here. Okay, so we also have some two separate scaling properties of disorder strength that I won't spend much long because I have end of my time. I would only say that okay, one can calculate linear, non-linear response functions also from these kinds of model and see that its behavior. And also, the next generalization one can ask for is an electron-electron interaction or electron-phonon interaction that contributes to the resistivity, and that can happen at higher temperature as well. Okay, thank you.
Questions?
Yeah, could you go back to this conductivity formula that you had?
You mean this one?
Yeah. So what is this thing? What is the GA and GP? If you could.
Okay, so sorry, I should have explained it. Yeah, these are the disorder mediated Green's function, where the thickness of this particular So this is a Lorentzian kind of. So the Lorentzian thickness is given by the disorder time scale. So and there corresponds to two different bands and I mean,
Oh, A and B are band labels.
band levels.
And you're saying it's a product of the imaginary parts.
Product of the imaginary parts, yeah.
Okay. Okay. The second thing is this finite length effects that you're talking about.
Yeah.
So there are various things that can happen, right? You can have like a surface to a bulk, scattering, and then if you have a finite length, you can also have a surface to surface scattering. Like
That's right.
There's a Fermi arc at the upper surface and there's a Fermi arc at the lower surface. Yeah. Could you characterize what is the relative strength of these two effects? Like, could you distinguish them within? I mean, you had some graph.
Yeah.
But which ones come from surface to bulk and which ones come from surface to surface?
I mean one. Okay, so one assumption we have actually seen is that from what we actually did here. So here you see that I mean its length dependence of this particular upturn where the interband scattering starts doesn't depend on this particular surface to surface scattering. So what we found is that as the states of the surface lies in two different surface and the length is something that overlap is very small. So that doesn't really show up in the conductivity plot. But surface to bulk, it has some probability of this scattering. So that actually shows up, and so that is why this separation to the first bulk band downwards is important, not the surface band.
So is it correct to say that the effects that you're seeing are power law in L and the surface to surface effects would be exponentially suppressed in L? Is that what you're saying? Because the overlaps, the surface modes exponentially decay.
Yeah. I think it will be exponentially separated because of the fact these particular wave functions have finite support. The wave functions in the surface states have finite support on the surface, then exponentially decays in the bulk. So it has the exponential dependence. So if one considers scattering between two surface states, so there will be some exponential fall.
Yes. Okay. Thanks.
Oh, can you go to that Fermi arc slide where you define Fermi arcs?
Yeah.
So you said that you think about this Fermi arcs as like you have some more surface modes at the upper surface, which are propagating in some direction, and surface modes in the lower surface, which are propagating in opposite direction, right? Yeah. So how I understand Fermi arcs in terms of these spectral weights, right? So
spectral weights by spectral weights.
Or the quasi-particle residue kind of thing. So you look in the momentum space and you have some spectral weight at some points, and you have a zero spectral weight at another point. So you don't have a closed Fermi contour, but some kind of. So how do you relate this picture to that picture?
I don't know that how to answer your question. So what I see is that just decrease the thickness.
Yeah, so that thickness, how do I see that thickness from here? So that thickness is something in momentum space, in kx, ky plane, right?
No, this thickness is not momentum space.
No, the Fermi arc length.
Fermi arc length is in a momentum space.
So
something like, so I have drawn a straight Fermi arc. So consider it to be a little curve here. And in the other surface, there is a little curve outwards because of the fact that it has some velocity in the opposite direction. Now decrease the thickness, and when it is very near to zero, it will see that the upper Fermi arc and the lower Fermi arc will form a complete Fermi loop.
So, sorry, I think
I think you can discuss later.
Okay.
Thank you, Nirnoy.